Aim of the experiment is to determine the specific heat capacity of aluminum by method of mixtures, and the materials that you need are you need a heater, you need a beaker, you need water, you need aluminum block, you need a styrofoam cup, you need a digital thermometer, and what else did I say? Scale. You need a scale, and that's it. So those are materials required. Now, what is the theory behind it? Theory behind it is the concept of specific heat capacity. Now, what is the meaning of specific heat capacity? You can write down the definition of specific capacity, which is something that is needed for the theory as well. So what is the definition of specific capacity? Specific heat capacity is defined as the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. That's called specific heat capacity. The amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. That's called specific heat capacity. Now, different substances have different specific heat capacities. So again, how much energy is needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius? So if I have 1 kilogram of any substance, okay, think of 1 kilogram of something. If I want its temperature to go up by 1 degree Celsius, how much energy do you need to put into it? That is called the specific heat capacity. Clear? Now, which substance in this universe has the highest specific capacity? Which substance in this universe has the highest specific heat capacity? Metal? Water. Water has the highest specific heat capacity, so it needs a lot of energy to warm it up. You need to take out a lot of energy to cool it down too. So it can store a lot of energy. That is why Florida and places which are surrounded by water, they are not going too much up and down in temperature. They're kind of steady, because during the day, sunlight falls on the water and all that, it picks up the heat and it holds on the heat. And the nighttime, it won't go too cold because the heat is still held there. The next day again, it picks it up. So the temperature is kind of maintained. Now, which places can go really cold or really hot is the dry places which is not surrounded by water. So water is very stabilizing. That is why places which are surrounded by water are generally very nice in temperature. It kind of holds the temperature. So if you look at Florida, like highest and lowest, that fluctuation is very little. Not like Louisville. Louisville can go 75 during the day and 30. I think there's a day that's coming up and it's going to go 30. Right? I don't know which day is Saturday. Something like that. So 75, 30. That kind of fluctuation cannot happen anywhere else, only in Louisville. All right, so the amount of energy needed. So water has got the highest amount of specific heat capacity, which means it will take a lot of energy for itself and then only warm up by 1 degree Celsius. That is why water is the best coolant. What do you put into your radiator? Water. It's primarily water, and then they put some antifreeze and and try not to freeze it. That's it. But primarily it is water. If you don't have anything else, you pour water. That's it. Because water can go into the engine, pick up a lot of heat, and yet not go up in temperature too much. Do you understand that part? Okay. So water has got the highest specific capacity, and the amount of the specific capacity of now symbol for specific capacity is C. C is a symbol for specific capacity. Now C of water is actually 4,200, approximately 4,186 joule per kilogram per degree Celsius. So 4,186 joules per kilogram per degree Celsius. Ice is only like half of that. So if you get burns, it's better to put your hand in water rather than touching on ice, because ice won't take much. You get it? Ice will take, but for it to melt. But before melting, it has to warm up. So the ice that you're getting is not necessarily at 0. It is probably at minus 20. So from minus 20, it will warm up to minus 19 only by taking around 2,000 joules. Whereas water will take this much to go up by 1 degree Celsius. Make sense? All right. So different substances have different things. Now, copper is like 390. That's it. So if you take 1 kilogram of copper, you can put 390 joules into it, and it will warm up by 1 degree Celsius quickly. So copper doesn't require much energy to warm up. So pans are given a lining of copper so that, you know, when heat is supplied, it will quickly go everywhere and make the heat even. Right? You understand? Different substances have different specific capacities. Mercury has got very little specific capacity because it should not take much. That's why mercury is used in thermometers, because it won't take much energy for itself to warm up, so it warms up quickly. Okay, same way gold. Its specific capacity, density is pretty good, very high, but it does not have much specific capacity. It's low. I know it's low, but I don't know exact numbers, but something must be in the hundreds. It's low specific capacity, which means it will not take too much energy from our bodies. So if you're putting a gold ring on, you won't feel it too cold for long. You understand? You take a steel ring and put it, you'll feel cold. Oh, it's cold, it's cold. Why? Because steel is taking more energy from your body, whereas gold won't do that. Right? So many things that you kind of take for granted, but there are sciences behind it. All right, so this is the basic idea of specific heat capacity. So 1 kilogram. So if there's a mass of 1 kilogram and you want to increase the temperature, delta T, if you want to increase the temperature by 1 degree Celsius, how much energy is needed? That's called C. Right? C is the energy needed to increase 1 kilogram's temperature by 1 degree Celsius. Now suppose you have 1 kilogram, but you have 2 degrees Celsius change in temperature. How much energy do you think is needed? To make it go by 1 degree Celsius, you need C amount, C. If you want to make it go 2 degrees, 2C. Yeah. And if it is 3 degrees Celsius, 3C. That goes accordingly. So if it is delta T, change in temperature, if the change in temperature is something called delta T, then it will be delta T, C. Right? What about 2 kilograms for delta T? It will be 2 times this. Not able to see it? I'll transfer it here. If it is 3 kilograms for delta T, how much energy will be required? Three delta T C. So if the mass is m kilograms, and if you want to make it go by delta T, it will be m delta T C or mc delta T. So this is the amount of energy needed to change the temperature of any substance. So this is your equation. Energy is equal to mc delta T. So if I want to question, okay, sorry.
I was just seeing down there.
Okay. If you want to boil a kettle of water, right? So we collect the water, and the water is initially at some temperature like 20 degrees Celsius, right? Just now you saw I just took water from there, so it must be around 20 degrees Celsius. And I want to boil it. I want to make it go up to 100. So what's the delta T? 80. So that is the 80 part of it. Now what I'm using is water, so the specific capacity is 4,186. How much mass did I use? Of course I didn't measure it, but you know how much it is. It should be around close to a liter, right? Close to a liter of water. So which is like 1 kilogram. So 1 kilogram times 4,186 times 80. That is the amount of energy that will require to start boiling. Is that clear? Okay. So that's the main concept here. Now let's come to the experiment. Our experiment. Our experiment is called method of mixture. So you understand the theory behind this? You can still continue the theory and the formula required right here still. Okay. So what we are going to do is this. We're going to take a cup of water, okay? And we'll check the temperature of the water's temperature, everything. We'll just monitor all the temperatures and all that stuff. Then you are going to have got 7 blocks there, so today you're all going to do it yourself. No excuses on this. You can just come there and take 1 block, quickly transfer it here. So when you transfer that hot block, which is at 100 degrees Celsius, into the cup that you put in, what's going to happen is there's a heat exchange that's taking place. Which one is losing heat? That block is going to lose heat when it goes here. And what's happening to this water? It's gaining heat. Now energy is conserved, right? It's not going to go anywhere. So the heat energy lost by that block should be equal to the heat energy gained by the water. Now what about the cup? Styrofoam has hardly any heat capacity. That is why we use styrofoam, so you can just ignore the cup. Ignore it. If I use a metal cup or something like that, or a ceramic cup, then of course I can't ignore it, because that also will absorb the energy from the block, right? But this cup is not going to absorb any energy from the... So the cup's specific capacity is literally like air. The density of this is almost like air, and the cup's specific capacity is almost like air. That is why when you touch this, so you look at this. I touch the table, find it cold. Why? Because your body temperature is high, and this one is lower, so there's heat flowing out, so you're losing. And when you lose heat, you feel cold. But when you touch the styrofoam cup, you don't feel cold at all. The reason, as soon as you touch it, yeah, what was the temperature of the cup? It was actually room temperature, right? But it definitely does not feel cold, because this will take a tiny bit of energy from your body and warm up to your body temperature quickly, and you won't even realize it. You don't even realize it because it took only a tiny amount of energy.
Is there a way to estimate heat capacity?
Of this?
Just like looking at different materials.
No, each one has got a number.
I know, but I mean, would you be able to estimate it just rank like do like that one has?
Oh, just looking at it? Nah. As I said, gold is pretty dense and heavy, but it's got very low specific capacity. Unless you work because it all depends on the electron vibration and the freedom of vibration in the atoms. That's what makes them store energy and all that. That you can't look at it and decide. Yeah. So, for example, if you take, let me ask you a question right here. You know, the wooden table, right? and the steel chair. Let's say there's a steel chair. Which one is at lower temperature? Wooden table or the steel chair? Which is at lower temperature? Same. It's very easy to fall into that. It is the same temperature, but does it feel the same? No, not at all. You sit on the steel chair, it will be cold. You feel cold. But you sit on a wooden chair, not much. And that makes you kind of feel that the steel chair is colder, the temperature is lower. No, they're all in this room for a long time, so it cannot be colder, right? But why is it different? Is because the amount of energy we lose on making contact, that's what makes you feel that that is low, right? Wood won't take much from your body, and so it feels kind of warm. So the best example is this. You open your refrigerator, take the tray of eggs, styrofoam tray of eggs, take it out from there. Touch the styrofoam. It doesn't feel cold at all. It came from the refrigerator, but it's not cold at all. Open it, take the egg. That feels cold. You see the feeling. The egg feels cold because it is sucking out energy from your body. This one did not take much energy from your body, so you don't feel anything at all. So that's why we use styrofoam here. In this thing, we are trying to use styrofoam because we are only talking about the heat exchanges between water and the block. That's it. Okay? So what is this, the theory behind our method of mixtures? Method of mixtures means this: when we transfer, this is water. When we transfer a hot block into this, heat lost by block is equal to heat gained by water. That's it. That is called the method of mixtures. Now, what is the formula for heat lost by anything or heat gained by anything? What's the formula? Heat lost by anything or heat gained by anything. What's the formula? I just mentioned it 10 minutes back. Yep, mass of block times specific capacity of block times delta T of block is supposed to be equal to mass of water times specific capacity of water times delta T of water. This is your equation. This is your formula. Now, what are you trying to find out here? We are trying to find out, so we can measure this, mass of block. We can measure the change of temperature the block is going through. We can measure the mass of water. We know the specific capacity of water, 4,186. We can measure the temperature change the water is going through. If you know all this, can you find CB? Right? So CB is MW CW delta TW over MB delta V delta TB. That's it. This is basically what you're doing through this experiment. All right? Any questions? So right there you can see that the aluminum is boiling. Yep, that is, I don't know if you can see. All right, that is a heater, and you have a lot of aluminum blocks heating up and boiling. And what's written on this? Is what we're trying to fill in. Okay, so what does it say first? That's our procedure / observation. So there's no table. This is your procedure / observation. So let me explain to you what you're supposed to be doing in the lab. Okay, so leave this aside. Now the procedure / observation is this. So what you're going to do is mass of empty cup, M1. How do you do it? Take this, weigh it. That's it. Mass of empty cup. Put down that answer in grams. We're going to work with all the masses in grams because you see, look at this. If you keep the mass of this block in grams, and if this is also kept in grams, you're fine, right? So it's fine. You don't have to convert to kilograms. So mass of the cup, empty cup, done. Then what do? You take this cup and fill some water. How much water should you fill in? As much as the block needs to get submerged. You don't want to put the block and the block kind of pops out. No, that is definitely not right. So the block should go inside. So I will say something like 3/4 of this. Something like 3/4 of this cup, or almost there, right? Pour the water, wait. That is the next step. Mass of cup plus water, which is M2. And then what do? You use a digital thermometer. I hope they work. It's almost a year. Obviously, it's not working. Thermometer can read Celsius and Fahrenheit. Before you take temperatures, make sure that it is set into degrees, okay, Celsius. And when you take any temperature of anything, always kind of mix it around because water is a poor conductor. So you have to drive the heat around, okay? So just kind of move it around like this. Don't poke it because this is sharp. So that's why I was looking for any holes in the cup. Because normally when you like poke it like that, it'll make a hole and then the water will come out, then you have to repeat the whole experiment. So the best thing to do is just kind of rinse, like, roll it around, but don't touch the block directly because the block being warmer, it will suddenly record a false reading. So the best thing to do is just kind of roll around. Okay, so we take the initial temperature of the water, then we take the initial temperature of the block, which is most probably 100. Most probably it's 100 because you can see it's already beginning to boil. So it should be around 100. We can double check that. Yeah, it should be fine. And then the transferring comes in. Transfer one block into the cup carefully and quickly. Carefully because you don't want to splash the water here. You don't want to like scoop a lot of hot water and pour it here. So that's why carefully and quickly. You can't like do it like, nice. Because if you, by the time you do that, it's already cooling down. So it goes here, it's already lost its energy. So your calculations can go wrong. So that's why very swiftly transfer it to the thing. And at the same time, start monitoring temperature and time. So basically you have to try and look at a temperature time. See how much time elapses. So as soon as you transfer it, note down the time. If this clock works, then you can go with that. So as soon as the needle comes to 12, you can just start off, put the block in. So we know it is approximately there, and then keep monitoring the temperature, and the time. Temperature, time. You don't have to record anything as it is, but just keep an eye on the time and keep an eye on the temperature. What will happen to the temperature? As soon as you drop it here and check the temperature will start climbing up. So let it climb. As long as it's climbing up, keep looking at the time as well. Maybe after a minute or so, you'll see the temperature is not climbing up anymore. Okay, you got it? After some time, you see the temperature is not growing anymore, which is probably around a minute. That is what you're supposed to put in here. Maximum temperature of the mixture, T3. That's what goes there. Okay? And then what do? Keep stirring it for the same amount of time it took for you to record temperature T3. Make sense? If it took around 1 minute for you to determine that the temperature is not changing any further, then you keep stirring it, the same action, and that's called a cooling process. So keep it cooling for the same time it took to heat, and the temperature may drop a little bit or may not, whatever it is. After the 1 minute time is over, record the temperature. It may sometimes be T4, same thing. It may drop a little bit by 0.2, 0.5, whatever it is, okay? Because heat is being lost, and we are trying to account for the loss. That's called cooling correction. So what's the cooling correction over there? The cooling correction is T3 minus T4 divided by 2. T3 minus T4 divided by 2. So if you look at this sheet, you get information. T3 minus T4 divided by 2. That's called the cooling correction. And now we need to find out what is the final corrected temperature of the mixture. It was not T3, but now you're going to add T3 with the correction. So T3 plus the correction will give you T5, which is our ultimate final temperature, taking into account the cooling correction. Make sense? And after the job is done, what you do is you take the cup with the water and with the block inside and wait the time. That is M3. That's the mass of the cup, the water, and the block all together. Done. Measurements are over. Now straight away to calculations. As I said, that is your equation. MB times CB times delta B delta TB, which is same as which is equal to this. And what is the mass of the block from the data that you have collected? The mass of the block obviously is M3 minus M2, right? Because M2 is cup and water, and M3 is cup, water, and block. So if you subtract those two, you will get the mass of the block. So you don't have to actually weigh the block. Subtract, you got it. CB, that's what you want to find out. Temperature TB, which is what? How much temperature change took place? How much temperature did that lose? Initially it was T2, and finally it became T5, so T2 minus T5. T2 is of course higher. Is equal to mass of water, which is M2 minus M1, times CW, which is 4,186, times change in temperature of the water. What was the temperature of water before? T1. And what's the temperature of the water afterwards? T5. So T5 minus T1, that will be the temperature. So if you have all those numbers, calculate CB, and that is your final answer. Are you ready for the experiment now? Of course, there are a lot of precautions, Celsius thing, and make sure that you handle that properly, and don't splash the water, and don't break the beaker, and all those precautions. But before you start the whole thing, let me show you some cool stuff which is part of your learning as well. This one is called a bimetallic strip. Okay, so if you go through the theory, you will understand what this is. This is called the bimetallic strip, which means what? There are two metals. Sorry, I should use a mask. I'm coming closer. I got my vaccination, so I'm safe. I don't want you to be safe also. Oh, my second shot was killing. I was down for 2 days, literally. I lost weight. Okay. This has got two metals. Like there's a metal piece here, and there's a metal piece here, and they're both welded together. So it's like two metal pieces together. That's called a bimetallic strip. What happens when you heat this metallic? Okay, so what is special about the two metals? Each one has different expansivity. That means they expand differently. One expands faster than the other. So what will happen is one expands faster than the other. One wants to go longer quickly. The other one doesn't want to go that long quickly. So, end result, like imagine there are people marching 3 by 3 or 2, like one here, like that, two by 2. They're marching, but the ones marching on this side, they want to walk faster. What will happen as the end result? Right? So this will bend. Because if I don't know which way it's going to bend, but if this one expands more than this, if this side expands more than this, then it will bend. I don't know which way it bends. Let's see. Let people for some time. You can see it bending. That's called a bimetallic strip. There's another one which is far faster. As soon as you touch it, it just curls like this. I was looking for it, I didn't find it. Yeah, so you can see it bent. It bent because this side expanded more than this side. And if I put water into it, you can see how it straightens up. Great. Okay, so this is the bimetallic strip. Where is it used? Where is the bimetallic strip used? Any idea where the bimetallic strips are used? You have used it, but you don't know where it is. You use it daily, but you don't know where it is. That's the beauty of my class. You learn something every day. When you go home, you'll be looking at things differently, right? So yeah, where? You have probably used it today. Think. Bimetallic strip. It's in your car. And if it fails, you're done. The car will seize if the bimetallic strip fails. Come on, starts with T, ends with stat. Huh? Starts with T and ends with stat. Thermostat. That's a silly way of saying it. Starts with T and ends with stat. Everyone will get it, right? Thermostat. Yeah, thermostat. You have handled so many thermostats. Like even on your range or whatever, you're setting the heating range, right? So you're kind of turning the knob and keeping it in a position. So what happens is the bimetallic strip is the one which actually heats. And when it heats, so if there is an electrical contact here, when it heats, it loses its electrical contact as soon as it bends away. Make sense? Just a short idea. Or electric iron. When you're using electric iron, you keep it on a certain setting according to the type of cloth. And you'll see as you're working with it, you can see it's turning off and turning on, turning off and turning on. Because as soon as the temperature becomes high, it actually kind of turns off, turns on, turns off, turns off. Same way, conditioning of the room, the temperature, control. It's the opposite for the cooling part. It's the opposite for the cooling part. When it becomes warm, it bends and makes a contact. And then the air conditioner will come on. And then as the air conditioner comes on, it actually bends less and less and less and then disconnects. Like that. So thermostat is something that's used everywhere. So in your car, you have thermostat. That's what tells the car that the thing is getting hot and start the fans and stuff like that. Now, if the thermostat fails, then fans won't understand when to come on, and then it will overheat the engines. Okay, and this one is another cool thing. It's a ball and socket. It also is something that demonstrates. It also is something that demonstrates thermal expansion. So I'm keeping this over here. So right now it is picking up the heat from the thing. It's not heating that fast. I wish it was. It is picking up the heat right now. So when it's picking up the heat, it is expanding. You can't literally see it expanding, but it is expanding. Okay? It is expanding. And this expansion, because it's expanding, it won't pass through the socket because the diameter changes. And that's exactly something that can happen in your car, the piston and the cylinder. if the cylinder, if the piston gets hot, its diameter goes bigger and finally it just gets stuck. Okay, so I don't know if it's heated enough, but the other heater that we had was far better. I don't know. I was looking for that heater. I don't know where it is gone. Have they flashed it? This is beautiful heater. And there were many in there. Okay. Yeah, should be enough. See? It's not able to pass through. It's not able to pass through. Because the diameter has grown. You can't see the diameter change, but the diameter has grown. Now when I cool it, it'll shrink back again. And then it should be able to pass through. Right? That's about thermal expansion. Okay, there we go. Now you can start your work. Now there are 5 thermometers.
Does the initial temperature of the block is like automatically 100?
Looks like it's not heating that fast, so I'll have to tell you what it is before you transfer. So that's why I will hold on to one. So do one thing, since you are 7, yeah? So let's say 4 of you will start the experiment with one set of thermometers, and you start with the work. And meanwhile, the others can get ready with the setup. Yeah, we can do it a little slow. Right. So 1, 2, 3, 4. Can you pass it on? Beautiful. No use for you. They'll get it. All right, so you can actually do the weighing step by step, maintain your CDC guidelines, whatever, and then I will tell you what the temperature of this thing is before we transfer it. Is it reading in grams or ounces? Grams. Not going too hot. Just around 3/4, not too much, not too less. Yours?
Yeah, sorry. Okay. Down for a second.
Well, I got an extra one then. Yeah, you all can just wait a little bit, so let them start their work and finish the work. All right, who wants to supply information to the video? Like,
show the paper.
yeah, show the. I'll face it downward so that whatever you're doing, just say it loud enough. Then, so basically, the transfer of the block is going to take place from here, and I'll just point it down. You can actually go to your seat down there, and then
How do you,
that is insane.
I know, but how do you get it to 0?
You don't go to 0. It's
Oh, it just
it's
like,
recording the temperature now.
oh, okay, that was stupid. Okay.
because this thing goes fast. So, you know, these things can actually go fast. So you just get ready with everything and then. I wish these things were working. Unfortunately, it's not working.
How long did you say it usually takes for this?
Oh no, for that you can take it right now.
Because it keeps changing.
What is it showing? It's changing. Okay, then
Yeah.
wait.
It
keeps going up.
If it is changing, just keep stirring it. Don't
Okay.
touch the metal part of the thermometer. It should steady the temperature. Normally in 30 seconds it should be done.
Okay, I think it's done now.
It won't take too long. So yeah. So you want to keep this
Show.
paper.
Yeah, I'm gonna show.
Is that too much water? Did y'all put more than that?
Alright.
Okay, so
Initial. You can just read it out. You want me
the
to lift this up?
initial mass of the cup is 4.1 grams. The initial mass of the cup plus the water is 269.8 grams. Let's see. The initial temperature of the water was 27.5 degrees Celsius.
You're going to transfer it from there. I can transfer you.
Okay.
You don't do it hard thing. So I'll transfer it, and as soon as you transfer it, yeah, you need to time. So keep an eye on that seconds thing. That should be more than enough. So I'm going to drop. So the temperature of this one is 97.0.
Is that for all of us?
No, it's just now as whoever
You can
is
take that.
transferring right
You can take that one. You already wrote it
now.
down.
Whoever is writing it down. Whoever is
You already wrote it down.
Yeah. As soon as it goes in, you record the temperature. Okay.
I thought you were gonna say I was like, that's smart.
Ready? And it comes 30 seconds. That's when I'm going to transfer. Oh, you're going to time this? Okay, that's good. Alright, you're ready. Now yours. The temperature is 97.1.
7.1. Okay.
Okay, ready with this?
Yes. Just let me know when.
Okay. You can go to your seat. Whoever is. Okay, you're not done. Okay, ready? Your temperature is 97.2, 97.3. So, you're in it? Oh, you got it. So your temperature is 97.2. Keep it inside. You're not supposed to take out the thermometer. Keep on stirring it.
Do we do it for another minute now?
Yeah, I mean like, yeah, did you go up at all?
Yes.
And keep it inside, more inside. More inside.
Oh, okay. Am I not supposed to put the
No,
block?
go inside there. Yeah, and then keep it there.
The block's in the way.
I know the block is in the way. But check the temperature properly and see if it is gone to a certain max. And that's what's supposed to be T3. Is it going more than that now or less?
More.
That means that was supposed to be T3. That's why you're taking the thing out. You're not supposed to take it out at all. The thermometer must be inside. At least by this much it should be inside. Never take it out. It's not a clinical thermometer. It's not like you look at the temperature. 32.8.
Mine hasn't
Is that
moved.
what 32 point?
No.
Okay, that's your part, this thing, right?
Yeah.
Okay, go ahead.
This one's right. Can I take it out now?
Yes, you can take it out. But weigh the whole thing before you.
Okay. So can I take it out? I want to be sure.
Once you weigh it, you're done with the thermometer. Oh, you're done with the thermometer. Yeah. You can start the thermometer,
Okay.
and you're done with the thermometer
Yes.
also. Did you change?
Yeah, it stops moving.
No. This one here. Oh, you have to do this one. So keep doing it.
Wait, how many times do you fit? Two.
No. This is the maximum event, and then after that you have to do the cooling for the same amount of time.
Oh, okay.
Whatever time it actually took to heat up to this.
Okay.
How long is it?
I'm like
2
almost
minutes?
2 minutes. Yeah.
2 minutes. Then keep doing that for 2 more minutes
Okay.
until it.
Okay.
You stir it.
I'm waiting.
Keep on stirring. Keep on stirring. Keep on stirring. Whatever you did earlier, you should keep doing the same action.
Stirred it 2 minutes now.
Is it bad if it didn't change that much?
But from where?
30.6 to 30.5.
That's fine.
That's
Even if
okay.
it's not changing, it's fine.
Okay.
Am I allowed to steal this thermometer?
You cannot go higher.
Yes.
Be lower.
Yeah.
Good. Ready? Temperature is 97.2. Take the temperature, take time. Take the time, and how long it takes to warm up. And if you, is it changing?
It is staying at the same. It went down.
So a little bit?
Yeah, it went down
That's
like 3.
expected, yes.
Okay.
How much did it go to?
It went all the way up to 33.8, and then
Yeah.
it's at like 30. It was at 33.5.
Okay, that's good. Now, pass this on. When you're ready for the block, bang. You gotta wait for some more time. Come on, go.
That's what my water initial is 32.3.
Oh.
Yeah,
Really?
that's what I had. 32.3.
This is hot water. You're picking it up from the hot water. That's all right.
That's cool.
That's strange. I expected this is a cold water.
So the way.
No, I didn't
This
realize.
never used to come hot at all, at all. I've never seen this come hot. Now they changed it. They fixed it. In other words.
Okay, so the initial temperature of the block was 97.3,
I got warm water in there, I can tell now.
and then the next one's 30.6,
You're in.
30.5,
You're in.
0.1, 30.7, 331.0,
Yeah, 97 years also.
Where did you put the?
Doing it. You're 30. The temperature of this one is
Should be wrong. Okay, those were wrong, so hold on. Okay.
Oh, I like how she's doing it on there. That's cute.
Okay, hold on.
7.9.
Okay, 233.6 minus 24 divided by 2.05. And then 25 is 2.6.
So I think this one is supposed to be.
Just keep an eye on that and see if it is.
Okay, these are the right numbers. I did it wrong the first time.
Okay.
I'm not gonna do this paper because
No. If it is not changing, then that is that's maximum temperature. Oh, you already got it. But if it is doing more than this, then you should record that. So, did you record it?
Okay, so this is the equation with the numbers plugged in before you do the math.
So we need to find CB.
Yeah, and find CB.
All right. And the CB is supposed to come approximately 900 joules per kilogram per degree Celsius.